Hi, I got a really interesting question on the Audio Bus forum recently. So let's have a look at it. The user SKRAT, I don't know if that's Scrat or SKRat. I'm going to paraphrase because taking it out of context will make it difficult to explain. From what I understand he's asking here is, if you have a plugin that's causing some aliasing artifacts, why doesn't the plugin developer oversample it so that you don't have to run at a higher sample rate? So I think he would like to run at 44 kilohertz all the time, and he wants the plugins to take care of their own aliasing so that he won't have to run at a higher sample rate. This is a question that brings up a lot of different thoughts, a lot of different issues. The first one is, yeah, the plugins should handle aliasing by themselves, but as we talked about in a previous video, it's not so easy to handle, and I haven't seen any that actually eliminate it when we're doing effects like saturation, distortion, overdrive. They tend to have quite a lot of aliasing. So you running at a higher sample rate is going to help them out, and then they're going to oversample, which will also help the situation. So that's one answer. But I think to get more directly into the question he's asking, we need to talk about why would we not want to oversample a plugin? Because I think there's an assumption in the question that oversampling doesn't cost anything, so let's just do it all the time. And that's the thing I want to talk about today. So without further ado, let's have a little demonstration where we look at what actually happens when you oversample something. So what have I got here? Let's have a look at this first. This file, if I zoom in on it, you will actually see there's something here. This is called an impulse. So I've scaled it so that it doesn't hit the peak, but the original data here was 1 followed by a lot of zeros. So we could define a digital impulse to be a 1 followed by infinitely many zeros, or practically 1 followed by enough zeros for us to see what we need to see. And that's what we see here. You can see this one sample is non-zero, and then it's followed by lots of, each of these little gray squares represents one sample. So what we're seeing here is the original impulse that I'm using as a test signal. Let's look at it in the frequency domain. This is very interesting. In fact, I'm going to have time domain and frequency domain together. What we see here is that the color indicates the volume in the frequency domain graph, and the color is the same color yellow all the way down from 0 hertz all the way up to 24 kilohertz, which indicates that this impulse has the same volume at every frequency. And that's why it's such a great signal to use for testing, is because first of all, it's really easy to make an impulse. You just, if you're working on a computer, you create a list of zeros, and then you set the first of them to 1 instead of 0, and then you have an impulse. And it's very useful to put this into all kinds of effects, whether they're filters I should say mostly filters is where it's useful, because if we can get an idea what happens to one sample when it goes through an effect, then we know what would happen to all of the samples, because whatever happened to one sample, they're all going to get treated. I almost want to say they all get treated the same way, but we have to back off a little bit. That's not necessarily true, and there are lots of examples where that's the case. But nevertheless, that's the idea: is that if you know what happened to one sample, and you know that the code is the same code for every sample, then you do get an idea what's happening to other samples just by looking at what happened to one of them. So here's my impulse, and today I'm going to take that impulse as input to an upsampler and a downsampler with nothing in between. So this code here is, I've commented out some things. It says gain boost here, but then I put a comment, which means I'm not gain boosting. I can even comment that to make it more clear. So here what I have, I'm generating well, this is a sine sweep. I have two functions doing the same thing. One of them puts a sine sweep through, and the other one puts an impulse through. And between these two signals, we get a lot of information about what the plugin does. So in this case, I'm generating a sine sweep, then I am upsampling, and then I am Here it says wave shape, but I'm not doing it. I commented it out. And then I'm downsampling. So that's it. I'm just upsampling, downsampling, and everything in between I've turned off. I'm not doing it. So let's have a look at what happens. Let's run this, and then let's have a look at what happens to my impulse. So these two graphs are just for me to make sure that I know things have exported correctly before I open them in Isotope. This is the first 2,000 samples of the sine sweep, and this is the first 256 samples of the impulse response. And let's get this up here, have a look at it. All right. So the impulse response is the output we get when you put an impulse in. And I'm looking at my impulse response, and the volume looks suspiciously quiet. And I think that I should do something about that. It is quiet because I'm scaling it down. And I see the real impulse has a maximum volume of about 0.6, so I'll just scale it from 1 to -1. And we'll rerun the script, and I'll get something that's not suspiciously quiet. Let's have that. There we go. Right, so this is the impulse response, which means this is the output and this is the input. And remember, once again, this test that I'm doing is not a plugin. It just upsampled the impulse and then downsampled, and nothing else happened. So this is a great way to figure out what kind of distortion is going to happen to your audio if you oversample. So here it goes. Let's zoom in and have a look in detail at what has happened to our impulse. Wow. It's a little bit hard to believe that this turned into this just from upsampling and downsampling. Let's talk about all of the changes we can see, because wow, there are a lot of changes. So the first change I notice is that there are 5 samples of delay. So this one started at the first sample, the impulse started. This output waited about 5 samples before we got any output out. I'm curious what I set for oversampling rate here. Now this one says 16 times oversampling, but I want to check my impulse response. Same thing here, 16 times. Okay, so that is what it is. Now it's important to note there are many different ways to do oversampling, and I'm using a method called IIR filters. IIR filters are filters that are similar to the way filtering is done in analog equipment, and the reason that I'm using those as opposed to the slightly, I want to say, let's say more commonly used FIR filters, which only exist in digital, is that I want to reduce this delay at the beginning. So let's talk about that for just a moment. If you use an FIR low-pass filter, the low-pass filter usually has this kind of shape that you see on the screen right now, except for it would tend to be much longer, so it might be more like this. Let's get the whole range. Plot range all. So it would look like this. The important thing to note about this filter, this is called the sync function, SINC, is that it's symmetrical and there's very low volume on the left and right side. Now I don't want to talk in depth about how this picture that I'm showing actually becomes a filter, but suffice it to say that if you see a filter kernel like this, this is the filter impulse response, which means that if I were to use this type of filter, which is a FIR filter, to filter this impulse, the output that I would get would look like this. And for me, that would be a problem. And it would be a problem because it delays my signal. So this, like the original impulse would have started here on the left side, but now I have to wait until I get halfway through this squiggly thing before the main part of the sound would come out. Another problem with this type of filter is that it will have some ringing that happens before the sound actually comes out. And that can be very audible if you have a moment of silence in your audio, and then there's like, and then the sound comes in. I shouldn't say very audible. The ringing would usually be at an extremely high frequency, which makes it less audible. But if you have ringing happening when nothing else is happening, that's not something I usually want. But my main problem with this is the delay. That if you really want to get a good oversampling factor, if you really want a good oversampler, you often have to introduce quite a lot of delay, which is fine if you're just mixing and mastering, but if you want to use it for real-time performance, that's almost out of the question to be having. I mean, you could be talking about adding 3 to 5 milliseconds of delay just for these filters. So I don't use that type of filter. I use this type of filter, and it has its own set of problems. But it doesn't have much, it doesn't have much delay at the beginning. So after the initial delay, what we see after that is this single sample of impulse has been replaced by several samples. I'm going to say it's till like about here. This is 17 samples of what I would call smearing. So it's called smearing because it's like you had this very precisely localized click, and then you spread it out from one sample length to a length of about 17 samples. So theoretically, if you would use this type of filter on your audio, you would lose a certain sort of crispness. And that's a little bit hard to describe because I'm not saying you're going to lose high frequency clarity. You won't. The high frequencies will be preserved well. But you don't have that clean timing like what you had before you oversampled. Now, I'm saying it like that, but going from one sample to 17 samples, 17 samples is not a lot of smearing. Let's talk about how much smearing that is. I'm going to get Google out so I can use a calculator. So 17 divided by 48,000 is the amount of time that this smearing represents. So this would be 1 second, this would be a tenth of a second, a hundredth of a second, a millisecond. This is 0.35 milliseconds. Is that audible? I think probably not. Is it going to be a problem? Probably not. But you should consider this in respect to the question that the user on the Audio Bus forum asked. If I have one plugin that does this, I don't think that's going to be a problem. But if I have 6 plugins in a chain, and all 6 plugins have a little bit of delay at the beginning, and then a little bit of smearing, like if this one smears by 17 samples, and then the next one smears by 10 samples, then I've now got twice as, not quite twice, let's make it easy. If this is 17 samples of smearing, and the next one is also 17 samples of smearing, I have now doubled my smearing problem. And every time you add another plugin that oversamples, you're going to smear it again until you will at some point have lost your impact, your ability to have a click that's just crisp and localized in time. It will still have the same frequency response, but instead of being click, it becomes more like s, which obviously isn't what you want. So this is the kind of thing where like you do it with one plugin, you oversample with one plugin, and you A/B compare it. You bypass the plugin and you listen. You're like, oh, I don't hear any difference, and you turn it back on, and you're like, no, it's doing a good job. But there's a danger that you could do that with 10 plugins, and each one you don't hear a difference when you turn it on or off. But by the time you get 10 of them linked up, there's a big difference. So that's one of the reasons why it's nice if you can get away without oversampling. If you have to use plugins that oversample, be aware of this. And be aware that the more of them you use, the more these little barely audible effects could potentially, well, they add up, and they may become audible at some point. Ultimately, your ears have to decide. But looking at these graphs is a good way just to inform your ears about what to listen for. Okay, so after that initial 17 samples of smearing, we transition into another phase of distortion. And that transition is marked by something very visible on the frequency domain thing. So you can see here that the initial smeared transient part of the signal has the same frequency response basically as the original does. It's equal volume from the bottom to the top. It's a little bit weird here. It looks like it lost some high frequencies, but it didn't lose them. It just moved them from here to over here. Mathematically, actually, we can prove that nothing has been lost. Frequency response is identical. But what's happened is that all of the high frequency energy that was lost up in this corner all gets delayed and pushed back later in the signal. And you can see it gets pushed back quite a long time. If we select this region, we're talking about 309 samples, or if I put this in time seconds, it's 6 milliseconds of smearing. However, that's smearing frequencies above 20 kilohertz, which hopefully isn't audible. So it looks really dangerous, but do we really care if frequencies that we can't hear get smeared? I don't know. I guess we'll have to, this is something you have to judge when you listen to your plugins. But once again, knowing this tells you what you need to listen for. Like if you're trying to decide if the oversampling is making things better or worse, know that one of the main places you're listening for, well, let's say the 3 places you're listening for are first, the initial delay. So if you're A/B comparing an oversampling versus not oversampling, you're checking to see if this delay is too much for you. And if you're not processing in real time, then forget about the delay, you don't care. The second thing you're checking is this smearing. Is that too much for you? And you can check that by listening to clicks. Or if you have a software like Isotope RX, you can actually make your own impulse response just by recording silence. So this is silence. And you can just take the first sample of a silent file and you can actually drag it with the mouse, and now I have an impulse. It's a little strange looking at this graph because it looks like it's waving up and down. Oh, it just stopped. Thank you, Isotope. Normally I configure my Isotope not to do those wavy lines. There's some logic to doing it, but I prefer not to see it, so I have mine configured this way. But if yours is making a wavy line when you move a sample, in the settings for this viewer, you can change the interpolation. I can show you that. Just, why is this view spectrogram settings? Yeah, it's not here. Okay, I'm not going to show you that. You'll have to go look for it. It's not in the spectrogram. It's in somewhere in preferences, and it's called interpolation. So what were we talking about? Right. So the first thing you're looking for is delay, and if you're not working in real time, you don't care about delay. The second thing is the smearing of the transients. So if you listen to a click that comes out of an impulse response, then you put it through a plugin, or even you have a click in a file player, and you are turning the plugin on and off, bypassing it and unbypassing it. You can listen to that click and see, is the click turning into a and if it is, well, maybe that you don't want to use that plugin with oversampling, or you want to turn the oversampling in the plugin off. The next thing that you want to listen for is this smearing of the ultra high frequencies, in this case frequencies above 24 kilohertz. Now if you're not a dog, you may not be able to hear that, and that's okay. Perhaps you want to get your dog in the studio and ask him to listen, or perhaps you just don't care. But anyway, at least you know what you're listening for. You're listening for after the click. There should be like a ringing, but it would be at that really unbelievably high frequency range. And if I was joking about being a dog, of course, but some people hear really high frequencies. I don't know if I can hear 24 kilohertz, but I do hear very, very near to 20K. Probably. I don't want to brag, especially about this, because I tried to listen to this audio while I was screencasting, and my screencasting software isn't set up for me to play in Isotope at the same time, so I'm not going to press play because my video will get messed up. Additionally, on YouTube, I'm almost sure this wouldn't get encoded, so there'd be nothing for you to hear even if I did play it. Anyway, so those are the issues we want to look at. Now, the next thing I want to talk about is what happens in the frequency domain as a result of oversampling. So in this case, this sine sweep that you're looking at, this is logarithmic sine sweep. It looks like nothing happened to it. Let's zoom in at the beginning, just make sure that delay is there. Indeed, do you see the delay? Let's zoom in on this axis. You can see there's that little 5 sample delay. I'm going to take my time format back to samples at the beginning, but it doesn't show up when you zoom out. And of course, 5 samples is not an audible delay. It's too small to be heard. Other than that, I don't see. There's a little something up here. Let's zoom in on this. This is interesting. We lose a little bit of gain at the top end. So from about this point until we hit the Nyquist frequency, the gain tapers off. And it looks like it tapers off by less than 1 decibel. So again, let's get the frequency domain view back up. We're talking about a frequency from 23 kilohertz up. We lost 1 decibel of gain. Even if you are a dog, I don't think you can hear 1 decibel of gain loss, so I'm not worried about that. In order to really see some of the issues that are going on in the frequency domain, it will be instructive for us to look at an example where something actually happens between the upsampling and the downsampling. All right, so here's the impulse response and the sine sweep, and this is coming out of a system where I have saturated, I've upsampled, I've saturated, and I've downsampled. So we looked at this saturator in a video last week. We were talking about whether or not it's possible to hit a saturator with 100 decibels of impulse input gain without aliasing, and this demonstrates that indeed it is possible. And so let's have a look at some of the interesting things we learned from this. So the main thing that I'm concerned about here is what happens right up at the top near the Nyquist frequency. So we have set that that setting in here and in here, so that my anti-aliasing filters are only allowed to alter the gain of the top 2.5% of the frequency of the spectrum. And if you look here at the just kind of eyeball the top of this waveform view, you can see that you don't see this tapering off at this corner, which is a little bit surprising to me the first time I saw it, because I expected that when we got up to 2.5, I want to zoom out so we can see everything. I had expected that when we got up to the top of the spectrum that we would start seeing a problem. This is why we're not seeing it, because I set my sine sweep to go up to 20 kilohertz. Let's fix that. I'll take my sine sweep right up to the top. Impulse response, saturator, sine sweep. There it is, and we're going up to 20. We're at 48 kilohertz. Let's go right up to 24. See what happens way up there. All right, let's redo it. The impulse response and the sine sweep. There we go, right up to 20 kilohertz, and now 24 kilohertz, sorry, which is the Nyquist frequency, and now we are seeing something. So the first thing I notice in the frequency domain is you see this little orange thing that's kind of jutting out from the corner. And this is only happening from like 22, 23 kilohertz up, and it's small, and I'm very sure I would not be able to hear that. But we do see this. This is clearly happening. The very last tail of this sine sweep has lost some of its volume. So that's where we've allowed that anti-aliasing filter some leeway to cut the volume down. And that's necessary because a filter can't just go up to a frequency and then cut flat at that frequency. It needs some gentle sloping to give it some time to get there, and so allowing it this what we're calling transition bandwidth here is absolutely necessary. And I'll show you what happens if we don't give it enough or if we give it too much. So one thing that someone might think is, you might go, well, I understand there has to be some bandwidth, but does it need to be 2.5%? So let's try like half of that. So I could just take this and divide it by 2. In fact, let's divide it by something a lot more than half. Let's divide it by 10. So now, I'll divide by 10, I could just add a 0 here. So now instead of 2.5%, I've got 0.25%, and I'm not allowing the anti-aliasing filters to do any distortion in the gain except for that region. So the first thing I notice, I don't know if you can see it, I think you can't see it in your view, is this. So I've got some debugging information that pops out on my Xcode screen, and this is showing me how many anti-aliasing filter coefficients that I'm getting. I'm using, for those of you who are really technical, I'm using all-pass filters, and I'm actually using second-order all-pass filters, but the numbers here are counting the number of first-order all-pass filters that I would need in order to implement this filtering scheme that it's calculating. So the first thing I notice is that when I narrowed down my requirement, that now I'm only allowing the anti-aliasing filter to alter the gain in 0.25% of the spectrum, that my number of filters that I've required has jumped up from 11 to 17, which means that it's going to take more time, it's going to use up more processor power, it's going to slow your computer down. But that's not a big deal. I think 17 filters, because I'm doing them as second order sections, you divide it by 2, that'd be like 18, that would be 9 second order filters. That would be equivalent, because I'm using a library called VDSP that comes from Apple, and it's machine language optimized to run 4 samples with a single command loader. So theoretically 4 times faster than ordinary code, but probably more like 2.5 times because of some other problems that I don't want to go into. The point being, these filters are the fastest filters that are available on iOS, and they are quite fast. So the amount of time I'm needing to do this, just the filtering part of the upsampling, is probably equivalent to like 3 or 4 Bell filters on an average EQ. And I say average because I think many of them are not using this machine language code because it's not very useful if you need your filters to be modulated. But of course these filters just stay in place, so it's fine for those. What was I talking about? Yes, so let's have a look at what happens to the gain of those high frequencies now that I have increased the strictness of my anti-aliasing filter requirements. So let's reload the sine sweep, and if we once more zoom in on this side, we see that the amount of gain reduction is less. So before, this curve was coming down, like down to here. It was maybe starting further out. I don't know if I have the same zoom I had before. But anyway, there's a little bit less loss in high frequency energy. But once again, it's instructive to view the frequency domain and time domain at the same time. So we don't see that energy loss happening until about here, which is like 23,500 hertz, and it's probably more than that. It's like almost at the top of 24 kilohertz before any reduction happens. Frankly, I don't care if we lose a little bit of energy at this frequency, because as we've talked about in other videos, when you get near the Nyquist frequency, what you're getting is mostly just noisy nonsense. You're not getting I hope nobody gets angry about me saying that. You're getting something that's quite distorted, and it's not going to be a clear representation of the original signal anyway, so you can afford to lose some of it. Okay, another interesting question is I said that I want 0.25, is that right? 0.25% of the frequency spectrum. The topmost 0.25% is the only part I'm allowing to be distorted. Is this really 0.25%? I think you'll see as I start adjusting this that it's probably not. It's probably actually less than that, because this is a very strict limit where when I say 0.25%, I'm saying that I do not want that filter to touch anything outside, which means that as soon as we hit the frequency where it's allowed to start messing with things, it's not going to immediately start making drastic changes. It has to have time before it, I should say it has to have frequency before it actually affects some difference. Okay, so it looks like I don't need that level of strictness, and in fact I don't want it, because as we look at the impulse response, we have a problem. When we looked at the impulse response of the other filters before, we saw a delay, and here I've got a delay, and then we saw some smearing, and here I've got some smearing, and then we saw this section, which is ringing. So we've got, once again, 3 artifacts of oversampling filters: delay, smearing, and ringing. The delay and smearing look like they're still okay, but this ringing, wow, that is a lot of ringing. Once again, it's ringing at above 23 kilohertz, and probably not, you probably can't hear that, but still I don't like to see it. It looks pretty bad on the graph. But let's have a look first at this delay, because there's something interesting here. When I had the filter, when I was allowing it more leeway to be free with messing with my gain a little bit, I was getting only 5 samples of delay, but now I'm getting 15. So this is something to be aware of, is the more strict your plugin developer is about trying to give you the full frequency range when you oversample, the more delay is introduced. And depending on how the plugins do delay, like I said, if they were using those FIR filters, they're going to get a lot of delay if they try to get this level of strictness, which once again, that's why we're not using them. So let's back off a little bit. Let's go back to the original setting, which was 0.25%, and let's just look at how the delay and the ringing change. I'm going to zoom out so that this is on the screen like this when I load the next version. Rerun the code, wait for it to output. Still waiting. There it goes. Drag that down a little bit and run the script that converts this to a WAV file and load the WAV files. So I'm gonna close this. Remember what it looks like, because now this is the 0.25%, and now I'm allowing. I wanted to do this fast so you don't have to remember. This is the weaker one. You can see the length of time that it's ringing is roughly the same. The delay is a little bit shorter. It's not a huge difference. Let's look at this delay, see how much shorter that got. So from here to here, it still looks like 15 samples. Did I really load anything here? Kind of perplexed by that. Reload this again. Okay, I'm suspicious, but perhaps those 2 filters have the same amount of delay. Still showing 15 samples, and I don't really see a big difference in the amount of ringing. It kind of looks the same, but there is a place you're going to notice a difference here. Let's pull a sine sweep up. So the place where we will notice the difference is, of course, if we zoom in on this end of the wave, you see this much bigger tapering off. It looks like it's lost about 4 3 or 4 dB of gain at the top over a wider section of frequencies. And this little spike here has come back. But the key place that I'm interested in looking at in the frequency domain here is that you see these distortion harmonics, which are good. These are this is the reason why we use a saturator, is to get these. They hit the Nyquist frequency and then they bounce off. You can see this one go up, and there's this little tick where you see kind of a blue cusp where it's bounced off, and that is aliasing. In the previous video, I was claiming that we have no aliasing, but we do have a very tiny amount there. So it will be interesting to know what happens if I relax even more. So now I'm going to allow not 2.5 but 25% of the spectrum to be distorted in terms of the gain. And we'll run this again. And you'll see that I'm allowing 25%, but it's not actually going to be destroyed over a 25% of the frequency range. It'll just have some very slight reduction in gain over that range. So let's reload. Here's the impulse response. Here's the sine sweep. Move that into review. Now you can see already when I've allowed 25% of the frequency spectrum to be distorted, that also introduced a lot more aliasing. You see these things where the harmonic bounces off the Nyquist frequency and then aliases back into the lower frequency range have become quite pronounced. And even the original main signal has bounced back and then been reflected back. It's kind of weird down here. And so we've now got quite considerable aliasing noise as a result of allowing the anti-aliasing filters to relax their strictness of how quickly they cut things off. But in exchange for that, we got a much better impulse response. Have a look at this. All the ringing is gone. So it turns out that ringing, we still have delay here. We still have smearing of the transient, but we've completely eliminated the ringing by going from 2.5% strictness up to relaxing down to 25% strictness. And that is certainly something beneficial that we ought to consider. So the reason why I'm showing you our plugin, and other plugin developers will do their upsampling and downsampling in a different way, but these issues are going to come up really no matter how they do it. I don't have it all ready for you to see an FIR upsampler, and I've sort of made a decision then as a plugin developer that my own personal goal is to make plugins that can be used as guitar effects. And since and you'll see a lot of the plugins that we make are very useful for other instruments, very useful for synths, for example. But I always want them to be able to be used in a live performance. I guess a guitar effect isn't exactly the right thing, but I'm a guitar player, not a keyboard player, so that's what concerns me. I want them to be able to use in a live performance. And in order to do that, it's really important that we don't have a huge delay at the beginning. So that's why, as we said before, we're never using FIR filters as our main method for upsampling and downsampling. But if we look at, let's zoom in on this impulse response. If we would look at this and just ask, okay, so a lot of plugins do use FIR filters, and what would this situation look like if we did? Basically what you would see is that you would see something quite similar to what we're seeing here, except it would be two-sided. So the characteristic of the IIR filter in the upsampler and downsampler is that there's this very short silence, and then there's this spike that comes from the spike in the impulse, and then there's some smearing, and then it's down. Whereas if you were using FIR filters, there would be some smearing on this side too. So the smearing would happen on the left and right sides, which means that there's smearing before the click and there's a little bit of smearing sound after the. The last thing I want to do is, I think we've seen two extremes that neither one of them represents an optimal situation. So with this very relaxed requirement on the filter, we've totally eliminated the Nyquist frequency ringing out of our impulse response, which is good because whatever happens to your impulse response is going to happen to everything. But we've also introduced quite a lot of, I wouldn't say a lot, but we've introduced more aliasing than I would like to see. If you look at other plugins, actually this is still less aliasing than what typically occurs, but maybe I'm being too picky. I just don't like to see that kind of stuff if I can get rid of it. So I would like to make this stricter. Let's go from 25% down to 5%. So I'm allowing 5% of the top frequencies to be reduced in volume a little bit in exchange for hopefully less aliasing and a little bit more ringing in the impulse response. Let's have a look at what we've got. Sine sweep off, impulse response off, and reload both of them. Let's look at the impulse response first. Our ringing is back. It's shorter than it was with the, I think it's shorter and smaller than it was with the 2.5% filter requirement, which is good. And let's have a look at what our aliasing looks like. This looks really good. Very, very tiny cusps up here. So now I'm thinking we could give it more than 5%. What about let's give it 10% leeway to mess with the top 10% of the frequency range. 10% is what frequency at 48 kilohertz. So 48 kilohertz, your Nyquist frequency is at 24 kilohertz. 10% of 24 is 2,400. So if we're giving it leeway to mess with the top 10%, we're saying from 24 down to 24 minus 2,400, that's between 22.6 kilohertz and 24 kilohertz. That's a frequency range I'm definitely willing to allow some distortion up there, because I'm very confident that that's not an audible frequency range. So let's convert to wave and reload the files. Impulse response. Now we've got some ringing, but this is really well managed ringing. It looks like basically the ringing is done within 125 samples, or let's get it in time format, 3 milliseconds. And this I guess this isn't that, I wasn't that careful about how I selected this. It's snap, my selection is snapping. Oh well, whatever. Let's put it like this. It's about 2 milliseconds of odd things happening, and then we're done with that. And what's going on in the frequency domain? A little bit of aliasing, but this is happening mostly above 20K. I would probably, if I were, well, I am actually adjusting this for a plugin, I would take it down just a little bit. I'm going to say let's give it leeway over 7.5% of the frequency range. So that would mean like 23 kilohertz and up is allowed to be distorted by the filter. Let's see what we've got. Impulse response, ringing as before, but not too bad. And this is acceptable, I think. So I'm going to stop there, and probably I'm going to use that setting. Well, we might make some adjustments when we release this plugin. I'd like to, just for marketing purposes, I'd like to be able to say 0 aliasing. But saying 0 aliasing means I'm going to have a lot of ringing, and in the impulse response, and I don't think it's going to sound good in a marketing slogan to say almost zero aliasing, and or if I were to say zero aliasing but ringing in the impulse response, that doesn't sound good. So oh well, we'll, as usual, we'll accept tiny little bit of hopefully inaudible artifacts up here above 20 kilohertz in exchange for a hopefully inaudible amount of ringing in the filter. So in conclusion, if you're interested in this kind of topic and you haven't subscribed to the channel, consider clicking subscribe, because then next time you're watching YouTube, if we have a new video, it's more likely to be prioritized in your video feed, and then you're more likely to notice it. So once again, thanks for watching, and I'll end the video here.